Hi everyone, and welcome to Replica. I'm Steve Astorino, Vice President of Development and Canada Lab Director. Helping our customers attain optimal insights from their data remains one of our top priorities at IBM. Today, we would like to share how a number of organizations are looking towards some of the latest technologies using AI to achieve this, namely synthetic data and digital twins. Together, these technologies can help organizations innovate at speed, lower operating costs and risks, and increase productivity during a time when real production data is becoming more challenging and risky to access because of GDPR and other regulations. We're going to learn through real-world use cases how organizations have been benefiting by uncovering new insights through AI-based solutions and digital twins of customer assets, and accelerating their time to value with quicker, richer, more complex data, resulting in smarter business outcomes. If you're a chief data officer, a CTO, a business lead, or a data scientist, then you're in the right place. So without further ado, let's hear from our first speaker.
Hi, this is Doug Henshin, Principal Analyst at Constellation Research. Synthetic data is a topic of interest for many companies. I want to share our perspective here at Constellation Research on why that is, where synthetic data is being applied, and who should care. Let's dive right in. Today's most innovative organizations want to drive better decisions and insights with the aid of artificial intelligence. It's a challenge that requires lots and lots of data in order to train the AI. Unfortunately, that data is often siloed and hard to access. It can also be subject to quality problems and security and privacy constraints. As a result, it's typically expensive, time-consuming, and in some cases impossible to compile real-world data at scale. Enter synthetic data, an increasingly popular approach through which high-scale data can be developed quickly and inexpensively. Synthetic data is generated by computers using techniques including simulation, generative adversarial networks or GANs, large language models, and other techniques. Synthetic data is often used in combination with real-world data, enabling training against both data types while boosting the size of the total training set. Synthetic data is not new, but its time has truly come, with faster, easier, and lower cost options now emerging even as growing security and privacy constraints make it that much harder to gather real-world data at scale. Now, synthetic data already accounts for nearly half of all data used in the development of AI, and Constellation Research predicts it will account for 90% of data used for training by 2030. Now, synthetic data is not just of interest to data scientists. It's important to line of business leaders who are trying to meet tight budgets and deadlines. Innovation teams all too often struggle to gather siloed data from across business processes and partner networks. Synthetic techniques enable these teams to quickly generate the high-scale data required to train models that spot risks and drive proactive recommendations. Chief data officers and chief security officers will also benefit from this trend. By using synthetic data that's based on real-world data, organizations can avoid using records that are subject to privacy regulations and data security concerns. In the pharmaceutical industry, for example, stringent privacy and data sharing restrictions make it hard for researchers to gather real-world genetic data. In the financial services industry, even when data masking and anonymization techniques are applied, 80% of credit card owners can be re-identified using just 3 transactional records. That's why credit card companies are using synthetic data to refine their fraud detection models. Synthetic data not only offers advantages in speed, scale, and cost, it supports the development of data tied to exception conditions and edge cases that rarely occur. For example, high-scale synthetic data is being used to train bots to spot customer service problems that only occasionally crop up in the real world. Similarly, simulated data can help organizations spot and trigger proactive responses to equipment malfunctions, process breakdowns, cyber attacks, and risk scenarios that are seldom, if ever, captured in real-world data. Now, if all these advantages sound too good to be true, you're not alone in wondering whether synthetic data can be trusted. The degree of similarity between synthetic data and real-world data is referred to as its fidelity. Now, researchers have ample evidence that advances in AI and deep learning have dramatically boosted the fidelity of synthetic data. But rest assured, the efficacy of synthetic data can be tested and proven. One way to measure fidelity is to run both synthetic data and real-world data against the same model for performance comparison. Another approach is to train one model using synthetic data and a second model using real-world data. Both models are then run against a third unseen data set to compare performance. To sum up, the speed, scale, and cost advantages of synthetic data, coupled with the elimination of security and privacy concerns, make it easy to see why this trend is rapidly gaining adoption. There's no doubt that synthetic data will be increasingly used in combination with real-world data to develop and deliver cutting-edge AI-powered applications and services. Thanks for watching, and I hope you found this valuable. This is Doug Henshin of Constellation Research, wishing you the best of luck as you begin your synthetic data journey.
Hello, my name is Simone Mangiante. I'm a researcher in Vodafone Group. And today I want to share with you the experience that my manager Günther Klaas and I have had with synthetic data in Vodafone. Synthetic data is currently a hot topic in the finance and banking sectors, where many companies have already production tools and teams dedicated to that. Our telco industry also lends a lot of opportunities to synthetic data. Many of our projects use machine learning and deep learning algorithms for use cases related to customers, for example, for churn prediction, and related to our network, for example, for traffic prediction. Therefore, we need a vast amount of data to train and test those algorithms. Data can come from our network equipment or from customer interactions, and it often includes private, sensitive information that are subject to regulation, with GDPR in Europe, for example. We have strong measures to protect the privacy of our data, and we should be proud of that. The downside is that sharing data gets complicated, and short-term and innovation projects lack much agility. We believe synthetic data can help accelerate data sharing and the pace of innovation, and we have been exploring two ways of generating synthetic data. Starting from samples of real data and starting from domain knowledge. In the rest of the talk, I'll describe these two methods, highlight pros and cons from our findings, and estimate their values for use cases close to telco service providers. In the first approach, we train a generative machine learning model, typically based on GANs, generative adversarial neural networks, with real data in a secure, controlled environment, so the model can learn statistical properties, correlations, and patterns. Then, we use the trained model to generate synthetic data that's now statistically similar to the real data, but it's fully anonymized and ready to be shared company-wide to other data scientists. We can also add differential privacy to the generator if we want to sacrifice some utility of synthetic data in favor of a stronger privacy. We have been exploring this approach for a while now, and we want to evolve our internal developments into an open, full-fledged synthetic data platform with help from academics and companies in this space. We can take a different route and use simulation instead of learning from real data. In this case, domain experts can model real-world systems as a set of agents that learn to simulate the correct behavior through reinforcement learning techniques. After initial training and while running, these agents produce realistic synthetic data that we can safely use for innovation projects. From the research we have done so far, generative models yield good results and seem mature enough in common use cases with simple tabular data input. There is still significant work to do with more complex sources like time series or specific datasets like type 2 tables. The main disadvantage is that these tools require real data. Therefore, they must be deployed in a controlled environment with data protection applied, and it's not straightforward or even not feasible to create a cloud-only platform. On the other hand, simulation models don't require any real data, but it's hard to get the necessary domain knowledge to build agents that can model the real world accurately enough. With simulation models, we are also free to perturb agents and generate what-if scenarios. And evaluation of the output data is a bit trickier for simulations, while an issue with generative models is to achieve a good balance between utility and privacy. To make everything more concrete, let's take an example of a common use case in our telco industry, predicting customer churn. We have brilliant data scientists who develop innovative machine learning algorithms for churn prediction and want to test them with real production data. Because of privacy and regulations, access to customer data is restricted, and we end up either with pseudonymized data not fit for purpose or too long approval processes that block our data scientists. Synthetic data can definitely help in this situation, and we have already tried out generative models successfully, and there's also room for simulating real customer behavior with reinforcement learning agents. Synthetic data can be shared freely across teams and countries, and our data scientists can improve machine learning models much faster, with the results of more accurate and valuable business outcomes. This is what we have done so far. If we look into the future of both approaches, we are pleased with the results of generative models and the ecosystem of players we discovered, so we want to push it further internally. We have just started exploring the simulation models with the help of IBM and Real Data platform, and we would like to include broader use cases, for instance, generated unstructured data like text or sentences. And we are looking forward to getting our hands on new and richer versions of the simulation tool to see where we can apply it. Thank you very much for listening. If you have had a similar experience, let's get in touch.
Thank you for taking the time to listen to my presentation. My name is Ted Lapas. I lead Satalia's data science team. We are a company focused on AI. We build algorithms for a very diverse array of problems. We focus on text, networks, time series data, different domains as well. We focus on future of work problems, logistics, retail, telecom, a very diverse landscape of work. I'm also an academic. I'm a professor at AUAB in Athens, in Greece. I would say simulation has been one of my key areas of expertise, key areas of focus over the past few years. And because of digital twins, we see a big sort of mainstream popularity of this domain nowadays, which is good for people like myself. So I was thinking of the best topic to present to you guys today, and I have a very quick presentation focused on how we use algorithms in Satalia to create realistic data, realistic synthetic data for different types of simulations and twins in our projects. So I have chosen, hopefully, a very intuitive domain to everyone here, the food delivery business. One of our ongoing projects, the customer, in this case, the client, is one of the biggest food delivery companies in the UK, if not the biggest. A very intuitive, I guess, setting. As a customer, you pick up your phone, you pick a restaurant, you pick the food you want to eat, you place the order, it goes to the restaurant, they prep your food, and then a driver, will go to the restaurant, pick up the order, and then take it to your house and deliver it basically to you. So that's the journey of an order, and that's how we typically design twins. We begin by mapping out the journey of every important entity in the ecosystem. In this case, the order is of course a very important one. Even though it seems simple and intuitive, if you look under the hood of how this happens in reality, in real life, it's actually way more complex. In this type of delivery systems, there's always a very complex algorithmic engine at the middle, at the core of everything, that makes the hard decisions. And in this space, this is basically what we call a dispatcher. And it has one very, very important job, and that job is to assign drivers to orders, to find the best driver for every possible order, and at the same time optimize across time and across multiple orders that arrive in a streaming fashion in the thousands throughout the day. So the dispatcher has to be very aware of the environment, of the distribution of orders as they arrive. It has to know about the drivers and needs to know where they are, how they behave, are they reliable, what's their speed. It needs to know basically all of these things about orders, about restaurants, about drivers, to make the best decision, the best assignment possible. And then of course you have to worry about the environment, things that might affect the dispatcher decision. So traffic, for example, weather. Is it a busy time in the area that you're focusing on because of, let's say, a big sports event? So all of these things have to be taken into account, and in the end, the dispatcher basically recommends assignments to drivers, but they can say no. They can basically reject the order and say, no, I will not accept this, I won't take the order to this basically location. If they say no, if a driver says no, the order goes back to the pile. It has to be basically reassigned in the next cycle. And this continues basically throughout the day, 24/7, every day of the year, until basically every order is assigned. So even after you assign a driver to the order, you still need to basically worry about what happens post-assignment, which basically is the driver has to go to the restaurant and they have to prep the food. They would drive to the restaurant, pick up the food from the restaurant, and then drive basically to the customer's house. So you have prep time, pickup time, and then the last mile delivery time to take into account. Now, this happens in real life, right? In real life, you have real data, so you don't have to worry about artificial data. But in a twin setting, in a simulation setting, you need to be able to create realistic substitutes for all of these sort of data creators, for these real life data creators. So you need to find a way to create realistic orders, realistic drivers, realistic traffic, and then of course realistic outcomes in terms of time, in terms of preparation time, delivery time, pickup time, and so on and so forth. So to create a complete twin and support what if scenarios, to support basically decisions, to make it useful, you need to be able to create realistic data for all of these stochastic parts of the ecosystem. Now, I'm going to focus on just one of these components because I don't have enough time to cover all of them. I will focus on drivers. Let's go a bit more into depth and see how drivers basically can be created. How can I create a population of realistic synthetic drivers? I need to basically take into account their location across space and time. So I need to know where they are. My synthetic driver, I need to know where they sit, where they exist, where they idle at any point in time. I need to know how they tend to move as well. I need to know, for example, do they tend to stay in one place? Do they tend to move around quite a bit? Do they go to specific places, neighborhoods? We see, for example, that drivers tend to idle around busy areas with many, many restaurants because they get more work there. Others have a different approach. They go to areas with less density, but less competition as well. Then you have vehicle types, scooters, cars, electric scooters, you have motorcycles, different types of vehicles. Then, like I said before, they can say no to assignments, so you have to be able to model their propensity to say yes or to say no to different types of orders. For example, some of them might not like to take late orders or not like to drive far away basically from their location. The reward you offer them is also a big factor. The order size, some of them may prefer not to, for example, carry large orders. The weather, the traffic, these all influence my choice to say yes or no to an assignment. Then you have the speed profile. Some people may drive faster than others, or they might be affected by distance, by the time of the day. Is it night? Is it daylight? And of course, reliability. Will you be on time? Some of them are more punctual, I guess, than others. So to create a realistic synthetic population of drivers, you cannot just create each of these elements independently. So you need to create drivers that respect the correlations across all of these profiles, all of these factors. And that's easier said than done, but that is basically what makes the game very interesting. So how can we do this? How can we basically look at historical data, look at what we know about the ecosystem, and create realistic synthetic data? Now, I will only go briefly over some of our key sort of methods that we use in this space in Satalia. The first one is resampling. So if you want to, for example, create, let's say, a synthetic Wednesday afternoon in August, you can go back to historical data and look for either the exact same context or similar context. And again, it could be time-based, space-based, how busy the area was at the time, was there a big event. So you build the context, and then you go to your database from the past, from the older data, and you try to rebuild the context and create a sampling bucket. So in this scenario, we don't actually create any new orders. We just resample from existing ones. But there is a very good option for many of these problems, and it is a great option for a version 1. I would say it's very scalable and very easy to implement compared to the others. Number 2, prediction. For many of these cases, for example, let's say you want to predict time to delivery, you can use a supervised model to predict that. The issue there is that models like that, they give you one output for every input. So if you give me the exact same input, I will always say, for example, 17 minutes. In real life, there's more variance. So we complement that with realistic noise that we wrap around the prediction. And then the last two options focus on basically density estimation across different dimensions. You try to have a distribution of what's happening across all dimensions, and then you try to sample from that distribution. Way more complex, but as well more mathematically robust, more interesting, and way more diverse. It allows you to create new elements that don't exist. It allows you to basically sample realistic, purely synthetic, never before seen data. Again, we use this quite a bit. I don't have enough time to go into depth, but hopefully it gets you a little bit curious about how we do things in practice. I'm going to end things here. Thank you for your time, and hopefully I'll get to see and answer your questions pretty soon. Again, thank you for taking the time.
Hi, I'm Ed Biddle. I'm a technical principal for IBM Expert Labs in Data and AI, and I'm a senior data scientist. I've been with IBM for the past 27 years. So there's a lot of buzz today around the use of synthetic data and digital twins, and how to do sort of what-if analysis. And so if you're considering this, I bet you're wondering what's involved, how long it takes. And so today I'd like to walk you through how we approach a proof of concept using the IBM Unreal Data product. And I'll bring the presentation to life by using a real use case of how Unreal Data could be used to help diagnose lung cancer. And the reason I'm walking you through a proof of concept is it's sort of think big, start small. And I think it's really important to get your head around how it all works and what you need to do before you start trying to expand and boil the ocean as such. And so what I'm going to talk you through is sort of the four main stages to doing a proof of concept using a digital twin. And it starts with a design, which is a sort of a 1-week activity. And the importance of the design is to really understand and tease out a business use case, and select one that allows you to, it will give you focus for the rest of the proof of concept. And without a solid use case, then the rest will become a lot more difficult. And if there's any questions or problems further down the line, then you always go back to the business use case, and that gives you the direction and the focus you need. So that's design. We then move into a 3-week discovery, and this is where we tease out all the sort of business logic that's required to help model the problem, the domain that you're looking to model, and this it's really important to have subject matter experts available to explain the detail. And if you think of our lung cancer sort of use case, and there's a lot of complexity from the medical side of things that we need to understand and capture that will allow for a decent digital twin. We then move into a 5-week build process, and this is it's an iterative cyclic sort of process like most of data science. And so we build our first digital twin, and then we improve and tune it. And then finally, at the end of the proof of concept, we do a playback and we share our results. We go through the story of what we've done. We look at the strengths and areas of improvement, and we define a set of next steps. So that's the overall flow of what we need to do. And now I'd like to go through each one of those in a little bit more detail. So if we start with the design, and to me, the design is really, really important. And so what IBM does, we use a concept or methodology called design thinking. And I think this is quite a popular methodology, not just in IBM. And so the purpose of design thinking is to really focus in on the business use case, and everything's from a business perspective. And we look at the end users, the people who are going to make use of the data that we're synthesizing, and we want to look at it from their perspective. So it's persona driven. You know, we look at what their to-be situation is today, what their pain points are, what they're trying to achieve, and then we come up with a to-be, you know, what's the ideal place that they'd like to be. And then we go through some what's called ideation to develop different ways of moving from as is to be, and that includes some wacky ideas as well. So no idea is a bad idea. And then at the end of the design thinking workshop, we then sort of plot feasibility against business value, and we down select a use case that's maximizes on, you know, feasibility and business value. So the idea is that we have one use case that comes out of the design thinking workshop. We then have a moment of pause, reflection, give everyone a chance to think about what we're going to do, and then we have a project kickoff. And in the project kickoff, we then do a deep dive into the business use case that we've decided on. We'll look at pulling out tasks that we need to do, and build up a backlog of tasks. So in IBM, we're very much we use an agile approach. So we build up a task list, a backlog, we split it up into hills and sprints and all that good stuff with agile. So the point of the project kickoff is to decompose the problem, come up with this task, and define the sprints that we're going to do moving forward with objectives and everything. The other important thing of the project kickoff is to define roles and responsibilities, and we encourage working with the customer and getting them embedded into our team so that they can be part of the process. And the other important thing is to set up logistics, so meetings, and what we need is a lot of access to subject matter experts, and by definition they're very busy people and so it's good to set up scheduled meetings so that we all know that we're going to get the access to them, and they know that they can put a time aside for us. also part of this sort of project kickoff is a bit of a training exercise where we get the team, everyone involved together, and we go through all the different tasks that we're going to need to do and how do we build and train a digital twin. So everyone knows what's expected of them and where the project's going. So once we've done the design, so we've defined our use case and we very much know what we're doing, who's doing it, when we're doing it, we then go into a discovery phase. And to me, this is the most important part of the whole POC. And it goes through, we have a number of user interviews. So this is interviewing the subject matter experts to really pull out the factors and the information that's really important around the domain that we're looking at. And so if we look at the lung cancer diagnosis use case, then lung cancer itself has some factors connected to it. It has a number of symptoms. It has tests related to it. It has treatments to treat lung cancer. So you can imagine that there's all these different factors that are interacting within the domain of lung cancer, and that's what we need to pull out and extract from the user interviews. But there's also the human side of things as well. So it's not just lung cancer, it's, how do people get lung cancer, and factors like, are they smokers? Are they exposed to pollution in their day-to-day living? Do they have other health conditions, their age? And all of this is really important information that we need to understand and capture by interviewing the experts who know all the stuff that happens in the medical domain. And so that's really what we're doing in the discovery. And then we're pulling out these factors, and then it's how do these factors link together. So if I'm a person and I have symptoms of lung cancer, then I might contact a doctor, and then I might go for a medical assessment. The medical assessment might say, no, there's no symptoms of lung cancer or no evidence of lung cancer, so you're okay. So that's one path, but there may be another path where they say, well, the tests there seems to be something, but we need to do further tests. And so you might go for different scans, and then those scans might have a result of, yeah, it looks like you've got lung cancer, and here's the treatments that we propose that you go through. So all the different factors are linked together, and we look at sort of event analysis as well. And this all helps build and define what the digital twin needs to model. And as I say, this is a really important phase to get all the information that's going to go in to build the digital twin. We then go into the build phase, which is our longest phase. It's 5 weeks in the plan. And as I say, like most of data science, you build your first digital twin, and then you test and validate it, and then you change and optimize it. And we'd be very unlikely to build our first digital twin and it being perfect. And so what we really need to do is make sure that in the test and validation, again, we're going back to the subject matter experts and saying, is this producing data that looks realistic, that is representative? Is this what you'd expect? And if it's not, then what could we do to change it? And then there may be factors that we just have overlooked that we haven't captured. And so we're going around several iterations to tune and optimize the data that's being produced by the digital twin, and training and adding new logic where needed to make sure that it's producing quality data that can really help with exploring the diagnosis of lung cancer in our sort of example. And then finally, once we've gone through our build phase, and I think it's really important to time box the build phase because you'll always be able to improve it. But we then come to our sort of final playback, and this sort of tells a story of what we've done. It captures and presents all the things that we've learned, all the inputs to the model and the outputs. It will say what looks and works good, and no doubt there'll be some weaknesses and areas that we want to improve or develop in our next steps. And this will say what we want is a task list of next steps in order to take our POC into the next stage. Thank you for your time today. I hope that was insightful. Thanks.
Hi, I'm James Talbot. I'm the Account Technical Leader for SGN, and today I'm with Stephen Fowler from SGN, Erwin Frank Schultz from IBM Consulting, and James Hope from IBM Client Engineering. And today we're going to be talking about an exciting project we're working on with SGN around digital twins of the gas network. So what I'm going to do is introduce a few questions around the team, and we'll get going. So Stephen, why is a digital twin important to SGN?
So from SGN's perspective, we're always trying to look at innovative solutions to various questions within the industry. And one of the main ones is around greening the gas and trying to meet carbon emissions and global warming and things like that. So we've got a number of projects that are running at the moment, one of which is the H100 hydrogen project up in Fife, which is powering a whole network of hundreds of houses for heating and cooking, etc., all using hydrogen itself. And this is going to help us really to sort of explore how a hydrogen system may work in the future. In addition to that, we're looking at using digital twins and join them together. So we've got the H100 digital twin, but we've also got a gas network digital twin. What that one allows us to do is to start to make better business decisions around the management of the network. As we go forward in time, we are going to be getting more and more different suppliers of energy coming in. So we're not going to be dealing just with gas, we're going to be looking at electrical plants demanding gas, so it's a multi-vector thing going on. One of the things with these digital twins is that they are able to sort of collect data from lots and lots of different sources, not just within SGN itself, but actually from other suppliers and other interested parties. And if we are able to bring all these things in together, we can actually address business concerns from SGN's perspective as well, because obviously we're interested in becoming an efficient and forward, moving company, but also to surface that information, to surface that data from lots of different sources, and push that out to other vendors, other suppliers, the government, etc.
So, Erwin, what is a digital twin, and why is it so important that this could change the industry?
So digital twin is a virtual representation of something that exists in the real world. In our case, we're going to be looking at gas networks, electrolyzers, assets, but it could be business processes, anything really. And a digital twin in theory could also be a design digital twin, so it could actually predate the real system. In our case, we're going to look at modeling systems that are being impacted by a lot of the drivers to net zero. As Steve had already mentioned, the move to converting energy from one vector to another, from electricity to hydrogen, and potentially back again via a fuel cell, are complex interactions, which brings me to the kind of second point, is that most digital twins actually these days span, certainly more than one line of business. In many cases like ours, multiple businesses that need to share data. So a digital twin models the real world, but to make it more than just a model, it needs to take data from the real world. So it takes instrumentation data usually from the real world to then model the behavior of the system, not just a static image of it, but the behavior of the system, and allows you to ask what-if questions. And then to pick up on another point that Steve made is the thing about business decisions. So ultimately, a digital twin has to improve the decision making that you, or the decisions that you make that have an impact back into the real world. So you've got this closed loop where you're taking data from the real world, you're modeling it, testing different scenarios, testing different decisions that you might want to make, and then picking the best one which impacts the real system.
If we go on to James Hope now, from a client engineering perspective, what is it we're doing? How are we actually creating this digital twin on a practical basis?
Yeah, one of the challenges for us was the sheer amount of domain knowledge and expertise that we needed to capture for this project. So we organised all that knowledge into epics, features and user stories, supported by IBM Consulting. And we prioritised 3 personas, Alex, who is a hydrogen production plant manager, Helen, who is a local authority planner, and Roger, who is a network operations manager. And we are in the process of building out an MVP, a prototype, for the first of those, Alex, the hydrogen production plant manager. To do that, we're using Cloud Pak for Integration as our integration platform, running on OpenShift in SGN's AWS environment. We have been working with our worldwide team as part of that project. We have also been working closely with IBM Unreal Data for synthetic data to use in that simulation. We've conceptualized the problem as a linear programming model. So to Erwin's point around modeling behavior, that's the way that we've approached it. It's an explainable approach. It's to optimize the hydrogen production plan, knowing information about the wind, the electricity grid pricing, and other factors like, for example, storage capacity, hydrogen production capacity, and those sorts of things. So we're looking forward to moving on and working to build out these other personas in the coming months.
So when we've done this, what's the next step? Where are we going to take this whole idea forward? What's the next view?
So from SGN's perspective, when we're in alpha phase at the moment, but what we've discovered as we've looked at alpha phase in quite a lot of detail, there's quite a lot of additional stories, additional personas that we think are quite valuable. And we think that by being able to present what we managed to achieve in alpha, but also having that sort of scope of what else is possible, that may well move into a much larger beta phase where we're able to incorporate more personas, more data sources, alluding going back to what Erwin was saying about bringing more data sets in, being able to model more situational analysis and decision-making processes using things like machine learning, AI techniques and things like that. And then moving eventually towards a sort of a productionized system, really.
So Erwin, Stephen mentioned alpha phase and beta phase. What does that mean?
So this project is part of a so-called SIF project, or is a SIF project, a Strategic Innovation Fund project, which is co-run by UKRI and Ofgem. And these projects, certainly for this round, have a 3-phase approach. So there's a discovery phase, a small phase in which you effectively just document the requirements. You don't build anything there. Then there's an alpha phase, which is about £500,000 worth, was limited to £500,000, and during that you expected to build a demonstrator of sorts and expand on the business benefits that the project ultimately would have. And then there's a beta phase, a potential third phase, and that is much more unlimited in scope. And that's where you'd actually go and build a digital twin, in our case proper.
Hey everybody, welcome to Replica. My name is Travis Hayes and I'm a strategic account representative at AWS. I've been at AWS for about 2.5 years, and in my entire time at AWS, I have been working with IBM to partner on how we build new solutions together, as well as drive business outcomes for our joint customers. I have the luxury of presenting to you today really AWS's view on how customers, how businesses can drive outcomes in value utilizing synthetic data as well as digital twins. So to highlight what we're going to talk about today, I really want to start with why now? Why is now the right time for you to invest time and resources in digital twins and synthetic data to gain value for your business? Then I want to move on to what we see as the 3 keys to unlocking business value with digital twins. Next, I want to talk really about real-world use cases that we see currently with customers, with AWS customers, of utilizing digital twins and the value that they gained. And then finally, I want to talk a little bit about how partnering with Unreal Data, IBM, and AWS can really help you drive value within your business on your digital twin journey. So to get started, I thought it might make sense for us to define digital twins. As you can see here, a digital twin is a living digital representation of a physical system that is dynamically updated to mimic the structure, state, and behavior of the physical system to drive business outcomes. Yes, that's a mouthful. The way I define digital twins is really the ability to replicate physical systems like a manufacturing or industrial plant, a wind farm, a solar farm, whatever it might be digitally. And by replicating that digitally, you can tweak the variables within that system, the inputs, the variables, to really understand how those tweaks drive greater efficiencies, reduce costs, reduce your carbon footprint, etc. Now that we understand really what a digital twin is, I want to talk about why now. We really have entered into a unique state in the world and in the technology that is out there today. First on why now is the prevalence of sensors. Never before have we had more sensors that are collecting data from the different components of our systems. Second is the ability to aggregate that data from those sensors utilizing IoT connectivity and services on AWS like our IoT services. Third is the modeling. Once we have the data from the sensors and we have aggregated the data utilizing IoT connectivity, we have the ability to model on that data and understand how changes in inputs can change the various outputs of a given system. And finally, at the root of all 3 of the previous ones is compute at scale. Through AWS's global footprint, we are able to provide compute at scale where businesses can scale up and scale down in order to meet their modeling needs and gain insight and visibility and value faster. Next, I want to talk a little bit about the 3 keys to unlocking business value that we see here at AWS. In order to get value utilizing digital twins and your general systems data, first you need to use data from disparate sources. Manufacturing companies have machines all over with sensors. Combining this data from all these different sources really creates a broad data set and a complete data set for us to operate and model on. The second is modeling the assets over their lifetime. And this goes hand in hand with building kind of that bigger picture data set. By modeling assets over their lifetime and not in narrow windows of time, you can better understand the full life cycle of a system, when it generally needs repairs, when it is operating at peak efficiency, etc. And third is really creating effective visualizations. By gathering the data and modeling the assets over their lifetime, you get all of this information, but we need a way to translate that information to end users that are not necessarily tech savvy, and that is done through visualizations. And creating these visualizations allow the individuals in the field or remote workers to take action based on the data that you have collected by understanding what that data is saying and directing them to make the right decisions for the business. Once customers have utilized these three keys and have really focused on these three keys to success, here are some of the business outcomes that they can realize. The first is improved asset performance. They start to reduce their asset costs as well as improve the efficiency of the assets by modeling the data and understanding how to tweak the various components to improve those cost as well as efficiencies. On the other hand, we have enhanced employee productivity. Employees are now able to spend their time in the most valuable areas by referencing the data that they get from the digital twin that they're operating with. Then, with digital twins, we have the ability to connect to remote experts. No longer do we need individuals in the field in front of the machines to make decisions that are best for the business. By looking at the digital twin, these remote experts can understand the system and what tweaks they need to make without being physically on the floor. But when you do need individuals on the floor, you do get those improved field services, improved uptime by utilizing the digital twin and understanding when those maintenance cycles might need to be implemented, what things might need to be fixed in the future. And finally, utilizing digital twins, businesses are able to reduce their carbon footprint. They're able to tweak the various components in a given system, the inputs, the variables, to reduce their overall carbon footprint and meet their carbon goals that are dictated by their business. Now that we've discussed what we view as the three keys to unlocking business value with digital twins, I want to talk about a real-world example. How are customers utilizing digital twins today to gain value out of their data and drive value for their business? And in this example, I want to talk about one of AWS's greatest partners, Carrier. Carrier came to AWS with a couple of challenges. First, they have buildings all around the globe of varying age with diverse equipment vendors as well as systems. And in each one of these buildings, there's thousands of assets that need to be monitored at a time. Second, all of these systems generate data, and the time series data, the transactional data, and the spatial data are all in disparate silos, and they really struggle to gain access to that data and gain real value out of the data. Their solution in working with AWS was to build Carrier.io. Carrier.io is a collection of turnkey services to create digital applications connected to carrier equipment and other devices. And by creating Carrier.io, Carrier was able to realize a couple of key business outcomes. First of all, Carrier.io created a shared service architecture and a shared service platform that teams around the globe could utilize in order to build applications on top of the data that was being generated by all of Carrier's building assets. Second, Carrier was able to monitor HVAC chilling across all of their buildings and reduce equipment downtime, optimize field maintenance, and predict cost based on the real-time data that was being generated by the sensors. And finally, by utilizing digital twins and their sensors and IoT and compute at scale, they're able to connect and visualize the data across all of their assets and provide building individuals an update on the health, safety, and comfort of the occupants of those facilities and their employees. Now that we've talked about the Carrier use case and the value that they saw, I want to talk a little bit about how partnering with Unreal Data, IBM, and AWS will help drive your digital twin strategy forward. Over the last year, I've been working with the Unreal Data team to really understand how a partnership between Unreal Data and AWS would help drive value for our customers. And what we learned over that time is that combining AWS's compute at scale in our global data centers, as well as Unreal Data's expertise in synthetic data, digital twins, and the metaverse, we could really create a product that will help drive our customers' digital twin strategy forward. By partnering with Unreal Data and AWS, our customers will be able to realize the benefit of improved asset efficiency, improved employee productivity, as well as gaining greater insight and value from the data that they have. If you're interested in learning more about the partnership between Unreal Data and AWS, I recommend you reach out to your local IBM representative or AWS representative to learn more. Thank you very much and enjoy the rest of Replica.
Hello, my name is Michelle Lu. I'm the co-founder of VSim. VSim is a simulation platform which is targeted at data center scale simulations. There are different definitions of digital twin. To me, digital twin is a simulated replica of physical model in the virtual environment. Digital twin can be applied to a vast range of applications, including manufacturing, engineering, medicals, robotics, digital human, etc. In the manufacturing domain, we may use a digital twin to cover the whole product cycle. This could involve using physical model during the design phase to rapidly iterate and optimize designs. It may also be used to optimize manufacturing, for example, to automate and streamline process. It can also be used to improve safety during manufacturing. Digital twins are used extensively in engineering and robotics. For example, simulating mechanical systems, simulating how different materials interact with each other, simulating structural strength, airflow, deformation, etc. Digital twin can also be used in medical field. For example, to train surgeons to perform surgeries using multi-physics simulations to model human tissue, organ, blood vessel, etc. They are also an important tool in drug discovery field by using molecular dynamics. Digital twin can also be used to simulate digital human. Digital human simulation can range from simple avatars in the virtual environment right through complex simulation involving hair, coding, muscle, skin, fat, tendon, etc., to form an extremely high-fidelity simulation. Simulating such a wide range of a complex model can be computationally expensive. especially if all those models are expected to interact with each other in a single complex environment. Furthermore, some of those models are so complicated, it's simply impossible to simulate using a single machine. Let me give you an example for that. We can simulate a human heart using the finite element method. However, in order to accurately represent a human heart, blood vessel, the blood flows through them. This requires to simulate a max number of elements, potentially ranging from hundreds of millions to billions. This scale of simulations may not be possible to run on a single machine simply due to memory constraint. Furthermore, such a large simulation may take too long to complete on a single machine. Of course, the performance requirements for digital twins can vary. While some digital twin applications may be satisfied with non-real time, many other applications may require user interactions. This means real-time simulation is critical for those applications. Our goal at VSim is to accelerate digital twin on a single machine by an order of magnitude compared with state-of-the-art simulators, and then scale up further by leveraging multi-nodes on the data center. As the scope of digital twin simulation is so large, another fundamental design principle we are embracing at VSim is to make it as easy as possible for other domain experts to inject their own custom simulations into a unified simulation framework. To this end, we have designed VSim from the ground up to be a component-based system. Although we are at an early stage in the development, we already have a prototype rigid body simulation running in VSim that is capable of simulating hundreds of thousands of rigid bodies in real time using mid-range consumer hardware. This is impressive, right? If you want to know more about VSim, please contact me. Thanks for listening. Bye-bye.
Hi, my name is Paul McDonald, technical co-founder here at Mero. I'm going to talk about how Mero is building the cleaning control center for commercial building. Commercial cleaning has changed forever. Cleaning standards are more demanding. Buildings' occupancy is changing every day, and the price of supplies and labor only continue to increase. That's why at Mero, we're creating a digital twin specifically for cleaning. And there are a couple of reasons for that. First, cleaning in commercial buildings demand perfection. Adopting new routines without a playground for testing can be risky, and if done wrong, can lead to tenant complaints and a subpar cleaning experience. That's why cleaning without Mero is often schedule-based, where cleaners clean areas without regard to whether or not the space has actually been used. In other words, the second floor might be cleaned 2 or 3 times a day, even if no one's used the space. Next, it's important to have the technology, but also the skill set needed for the proper execution of the data. And that's when industry experience when adopting smart initiatives come in. It's quite commonplace now to have lots of IoT sensors throughout the building, each with their own data points. The problem is what to do with that data to drive change. At Mero, we didn't stop at the digital twin, but offer a consultative approach to actioning the data to create a more dynamic and cost-effective cleaning program. Lastly, interoperability between systems is so important. Collecting all of this smart IoT data means we cannot have data silos. And that's why insights from Mero can feed seamlessly into other systems. When customers adopt Mero, they're not just adopting new tools for smart cleaning, but integrating that data into other digital twins or IoT systems a building might already have. This allows customers to use the Mero data for not only cleaning, but for other smart building initiatives across their organization. So to dive in on how we accomplish this here at Mero, first, we deploy IoT devices to capture cleaning activities within a space. We also bring site teams to buildings to survey the building and create a version of it within the Mero system. We combine those two data sets into our homegrown data science infrastructure. And I want to narrow in on that infrastructure a little bit because it's something we're really proud of at Mero. By allowing the data team to work autonomously and leveraging some really great cloud technologies, we're allowing the data team to quickly build models, see their outputs, and then put those outputs back into the infrastructure in a recursive process. This allows us to test our models against real and synthetic data sets really quickly without DevOps or web development teams needing to push changes. Every building is unique with unique cleaning patterns. And that's why the end result of our model is the ability to rapidly prototype cleaning outcomes that are specific to that building. Again, by taking live and simulated cleaning data, we're able to change cleaning behaviors to save buildings money and delivering on an amazing tenant experience. We call it changing from a static cleaning model to a dynamic cleaning model. To go a little bit more about our sensors, first we have our traffic monitoring product, a peel and stick, battery-powered, 95% accurate sensor that tracks in and out an occupancy in a building. We also have our supply monitoring sensor. Again, peel and stick, battery-powered, and retrofit into existing dispensers to wirelessly communicate dispensing levels of things like paper towel and toilet paper. Lastly, we have our cleaner location product, which gives exact locations of cleaners as they perform tasks throughout the building. Now, from a customer point of view, again, peel and stick sensors that can be installed by anyone in less than 30 seconds. As I talked about earlier with our data science infrastructure, we model and make suggestions on how cleaning can be improved. For example, avoid a certain space since no people have been in it. Cleaners are directed to change their behaviors in our smart cleaning routing application, which again applies the insights that we talked about earlier. The end result of all of this is real-time insights through our dashboard application, which managers can use to feel confident in their Mero-powered cleaning program. Now, changing from routine-based to dynamic cleaning brings real cost savings. Traditionally, as we talked about earlier, again, cleaners will enter into an area whether it needs to be cleaned or not. And that causes wastage of consumables. Mero allows cleaners to clean areas at the perfect time, allowing customers to save up to 35% in supplies while ensuring tenants never encounter an empty roll. And this dynamic cleaning doesn't only extend to consumable savings, but on labor savings as well. In light of cleaner shortages, companies can clean more effectively and to scope more than what was ever possible on a traditional cleaning routine. This process can save buildings upwards of $1 million on labor costs alone. Thank you so much for listening. Again, my name is Cole McDonald, technical co-founder here at Mero, and you can check us out online at mero.co.
Hi again. After hearing some great examples across tech, energy, telco, and research analysts, we hope you have valued and learned from our guest speakers today. For me, the emerging importance and value of synthetic data and digital twins to the enterprise can provide a competitive differential for organizations. Synthetic data is helping companies unsilo and reinforce their real data to drive better insights, resulting in enhanced decision-making and smarter business outcomes. And digital twins, specifically digital twins of customer assets, are helping companies model and simulate real-world conditions so they can respond quicker and more effectively than before to ever-changing business environments and market conditions. We hope you've enjoyed the show. That is it for Replica 2022. Thank you for attending. We will see you next year.